As I mentioned, for those of you that didn't quite get up here fast enough, we're going through a big, huge pile. We just go through it once. But at the end of class, if you didn't get up here fast enough at the beginning of class, we'll hand you your printouts at the end of class. Hopefully, we dismiss a little bit early. Now, I want to point out a couple things about these printouts that you just got. First of all, the printout is based on 45 points, not 50. The exam is 50 points. But the Scantron guy that grades all the Scantrons, he doesn't know anything about our clickers. He just knows there's 45 dots, and that's what you've got. So the percentage that you see at the top of the paper is not accurate. What you have to do is add up your Scantron and your clicking, which is already posted in web courses, and then that'll be your total. And then multiply it. It's a 50-point test, so multiply that by 2. And that'll be the percentage you get on the test. The raw score is correct. That's how many questions you got correct. All right, so just keep that in mind. And that'll always be the case. Whenever I use clicking for a few questions, which I like to do, and I usually do, then the Scantron printout is not quite accurate. Now, I want you to look for a couple errors that are very common with the Scantron printouts. First of all, actually before that, let me just make a point. I think I forgot to say this in the previous class, but let me say it now for you guys. If you looked in your grades page and you see a -1, what that means is your Scantron didn't get graded. If it's for the clicking subtotal, that means you don't have a registered clicker. Okay, or you didn't bring your clicker. Now, that being the case, if you have a -1, we may have just figured out, my TA in the first hour figured out all the people that had Scantron problems. So if you looked at your grades page and it said -1 for your Scantron grade, you don't have a printout today, that means that it was a blooper with your PID or something, or the test form. Okay, so we'll figure that out if you have a grade, because we have your Scantron, hopefully, and so we'll get that done. Now, the other thing about the Scantron bubbling errors, look on your printout and see if there's any one question or more than one that's marked that's blank. All right. Anybody have a blank on their printout? There's frequently one or two. Okay, one guy. Couple, okay, I see. All right, the other thing I want you to look for is look to see if you have 2 answers for the same question. It should be obvious just scanning your list of answers. All right, anybody have doubles? 2 answers. Because 2 answers is going to be marked wrong. Okay. What I want you to do, those of you that have the blanks or doubles, come bring them up here to Caroline, and she'll bring them right now. Bring them up right now. And we'll try to get them sorted out and checked. And before you do the notes, can you check the Scantrons? All right. And we'll just get those, try to get them sorted out. And hopefully you guys that just gave me your printouts will try to get them back to you at the end of class. Because Caroline's she's gonna dig through the gigantic pile of Scantrons, which I think these are the Scantrons. And actually they're at the top. Now, you may be asking yourself, Dr. B, what are these printouts good for? I mean, they're nice. They show me all the questions I got incorrect. They show me all the questions I got correct and incorrect. What do you use them for? Well, if you go onto the website and look at the blurb files, there's a new page in Web Courses. This is what it looks like. You can download a little blurb about your test. Now, it goes by test form. Test form A, test form B, test form C. Right? So if you go to the section 2 column that's over here, you guys, I had 3 test forms running in this class. So at the top of your printout, it'll say form A or form B or something like that. Then you download the form A PDF, and that'll give you a little blurb about each question. Now, with those blurbs, you can actually make a nice little study guide for the final, because you'll know the gist of each question that you got incorrect. So if you look at your printout and then look at the blurb file and you see a pattern, like you messed up a lot of third law questions, well then on the final, you'll want to make sure to use a little extra time to study third law, Newton's third law, or whatever the topic is. All right, so the combination of your printout and the blurb file will really help you study for the final. Also, just so you know, the blurbs, you'll see it as soon as you download it. It's just for every question except the matching. The matching, there's no way for me to put a little blurb in on the matching, but that's just the formulas. Anyways, so the true, false, multiple choice all have blurbs. They're not verbatim. It's not the question itself. I don't do that. If I wanted to do that, I would just let you carry the exam out of the lecture hall. But we don't do that. We hand the test forms back in. All right? That's physics department practice. But I give you a little blurb for each question, so it won't. You may remember it pretty well, but if you don't, the blurb will tell you the basic area that you have to study. Also, there's a blurb for the drop distance calculation. That was number 2 in the clicking. And there's a separate PDF for the velocity graph brain burner. And those are also in Web Courses in the talking PDF pages. And you can definitely look at those. Okay, questions about blurbs? Okay, let's keep going. Some more study tools. I want to point out to you that in the textbook we have something called highlights or highlighters. I see it written different ways. And you can actually subscribe to them. And hopefully you're using them yourself to study. But if you have the ebook activated, you can make highlights. And you can actually look at my highlights. Okay. Now here's I just did a screen grab this morning of the textbook. This is from chapter 4. This is from the topic we're going to be talking about today. Right up here is a little it looks like a yellow sticky note, and that indicates that there's a little highlight there. And the highlight is this kind of pinkish text here that I highlighted in pink. And then if you click that little sticky note, or if you click on this little list down here, you'll pop out the actual note that I typed in. And sometimes my highlights are pretty long, and I even put a little equation in there and stuff. And you can actually subscribe to those and look at them. And another nice thing about it is you can take the sticky note and you can actually copy and paste into a separate notes file, so like a text file or word processor file or something like that, if you like to do that. I see some of you guys writing out notes or rewriting your notes and stuff on a big word processor and stuff. It's nice. So if you want to do that, it's kind of helpful. And you can subscribe to my highlights by using my email address. Now, this is not my true email address. It's my vitalsource.com throwaway email address. It's right here. Let me magnify that for you. brewbeckner@knights.ucf.edu. Yes, it's deliberately misspelled. And no, I don't actually use it for anything except phony accounts or phony email addresses for different accounts that I have to use, set up and stuff. So I've used this for throwaway email for, I don't even check it. Matter of fact, I can't even remember how to check it. But I'm sure I could look it up if I had to. But don't send me any email there. But do use that to subscribe to my highlights. And remember, you may be sitting in class every day and just thinking, oh, if he would just stop talking that Dr. B, all that hot air, and I'm just not really getting this stuff. You may find that if you subscribe to I see a bunch of you guys smiling when I say that. Good. I'll remember that. Anyways, I try to be humble about class and stuff, so I know it's sometimes boring for you guys. But anyways, the highlights, you may like how I write things out in the highlights, and that may help you click a little bit more than listen to me drone on endlessly about Newton's laws and all that stuff in class. So it's just another communication channel, and hopefully for you it'll be helpful. Okay, so you're welcome to try it. And the way it works is at the lower left of your bookshelf software, there's a little icon. It looks like a little person or a little face or something like that. And you click on that, and it'll ask you for if you have friends or something like that. And then you type in this phony email address, and you can subscribe to my highlights. Questions about that? Yes.
So you said you subscribe through a button on the lower
left somewhere. It looks like a little face or something like that. I don't know. It might be. I'm not sure if it's in the book or if it's in the lower level dialog box. The one that you get when you open the application. Anyways, it's in there somewhere. I have the teacher's version of the software, so it's hard for me to know how it works for you guys, but it's something like that, I think. All right, last Tuesday, we talked about centripetal force, centripetal acceleration. And hey, you guys, this is what we were working on, this proportion, these two triangles. And I just want to, draw that back to your attention. And I also want to mention that when we did that, and also homework 5, we were actually doing what I like to call visual calculus. In other words, we were doing the same thing visually. We were thinking visually through the matter the same way a mathematician teaching a math class or a physicist teaching a fancy physics class with calculus would do it. Now, you didn't see any of the fancy calculus equations, but you did see the diagrams and stuff that if I would use the same diagrams if I was teaching Physics 1 for scientists and engineers with calculus. All right, I guess that's another way to put it. All right, so it was and the visual stuff is actually the important stuff. The formulas, I don't want you guys to feel like, and some of you might not, and some of you have had calculus, but some of you might think, gee, I just suck so badly at math, but you may be inexperienced at math, but I don't want you to think of yourselves as dumb in any way. Not a single one of you. Because the formulas are not the hard part of calculus. It's the thinking. And to do those diagrams and follow those diagrams, you have to really think. And that is the hard part. Einstein said this famous saying of his, if we knew what we were doing, it would not be called research. Think about that. That's Einstein saying that. Smartest guy of the 20th century, right? And that's what he said. And so everybody struggles with these concepts the first time they get them. It's just that, Einstein struggled with E equals MC. Who knows? He was probably trying E equals MC to the third. No, that doesn't work. E equals MC to the fourth. No, that doesn't work. And then somebody got him squared away with E equals MC squared, And we all struggle. So tell your folks you did some calculus the other day. Because you did. Okay, visual summary of what we did. I want to go through this quickly. On a perfectly circular orbit, a uniform circular motion type orbit, the acceleration is centripetal, the velocity is tangential. The distance to the center of the path is the radius r. Centripetal acceleration form, as we mentioned last time, v squared over r. We had a couple easy questions on this on the test. We're going to be doing a little more centripetal force stuff today. And just to make a note to you, in the centripetal force or centripetal acceleration formula, the velocity, or the square of the speed, v squared in the numerator, that is something, if you're in a car on a circular track, that's something that you control with the gas and with the brakes. You hit the gas. If you go a little too fast for what you want, you hit the brakes a little bit, bring it back down, then you set the cruise control. The other thing is the r, the radius of curvature, is set by the design of the track. So the guys, for instance, that designed and built the Nardo ring, they had a very specific radius that they wanted to use. So that was part of the design. If you go to Daytona International Super Speedway, which I've never been there, I've driven past it a number of times, but I know that they have very precise specs for the curves, the banking angle, and all that stuff. Most of those NASCAR places, they have it all squared away and all specced out. So that's the centripetal formula. Now, we're going to connect centripetal acceleration, centripetal force, to this concept of universal gravitation developed by Sir Isaac Newton. And what he said was that the force of gravity, which everybody knew in his day, that gravity is a force that pulls downward, but nobody had it figured out. What controls gravity? What are the important factors? Does the day of the week matter? Does the weather matter? Does the density of the object matter? Does the size of the object matter? What matters? He figured out, or his theoretical conjecture was that the mass and their distance apart for any two objects it controls everything about the size and the direction. The geometry controls the direction. It's always attractive. So it's from one object towards the other one. But those are the two physical factors that determine the size of the force. And he said the more mass you have for either object, the more force. So the Earth is going to produce a lot of force, but then you also have a lot of crushing force from a bowling ball compared to a ping pong ball, because a ping pong ball has less mass. All right. So if you let a bowling ball drop 1 inch onto your little finger, it's going to hurt a lot more. It has a lot more force than a ping pong ball dropped on the same finger. The ping pong ball, doesn't do anything, right? He also said, I think that the geometric structure. Oh, did I say geometry? Yeah. He was following Galileo's procedure, the mathematical language of nature. He said, in this particular case, Ellen, the mathematical nature of the universe means that distance matter, and it's going to be in the denominator somewhere, because the more distance, the weaker the force, is what he figured. You know, because he was thinking about the moon. He was thinking about the force that keeps the moon in its orbit and the acceleration that keeps the moon in its orbit. And he thought to himself, you know, I think that the same thing that pulls an apple from an apple tree down to the ground is the same force that keeps the moon centripetally on its circular orbit. And this is the force law that he came up with. Go ahead and write it down carefully. We're going to be spending a lot of time on it today. The force of gravity is equal to the ratio of mass 1 times mass 2 and a conversion factor, capital G, also known as the gravitational constant or Newton's constant, divided by, in the denominator, r squared. R is the separation between the two objects. Mass 1 is the mass of the first object. Mass 2 is the mass of the second object. And then r is the distance between mass 1 and mass 2. And Sir Isaac Newton said, this will explain everything. He said it'll explain the acceleration of an apple. It'll explain the path of a cannonball along a parabola. It'll explain the orbit of the moon around the Earth. They knew the distance to the moon in terms of the radius of the Earth and everything. And they knew the time that it takes to make a lap. So they knew v squared over r for the moon. And so he was able to figure out, yeah, if this is my force law, then the moon's orbit is perfectly in line with centripetal force and this force law. The moon is on it's pretty close to circular. It's just a little bit elliptical. It's pretty close to a circle. And he said, yeah, this thing I got it. This is the form of the force. So he didn't say it's 1 over r to the third, or 1 over r to the fourth, or 1 over r to the fifth, or any other, just 1 over r squared. Now, I'm going to work through an example with you of the forces on a satellite. And this example is going to put together or synthesize the idea of centripetal force and the idea of universal gravitational force. All right? So here we go. Let's say, for example, that we have a satellite of mass m subscript s and the mass of the Earth. And the satellite is going to interact with Earth. You know, the satellite doesn't orbit the rocket. It doesn't orbit your car, but it does orbit the Earth. Earth is big enough to cause an orbit, so let's look at it. Now, if you're down there in NASA at mission control and you're trying to lay out the orbit, trying to design the rockets and everything, first thing you got to know is, where do you want to put the orbit? You want it up there a couple hundred miles where the space station is, or do you want it way out there? You know, where they have a bunch of other satellites way out there in space. Or do you want it out there at the moon? Do you want it orbiting the sun? You know, do you want to send it out? Do you want to send it to Mars and then orbit around Mars and stuff like that? So to do this, yeah, you want to know where you want to go, and then you figure out, you know, what kind of rocket do I need to get there? Right? So that's the basic stuff NASA is concerned with. Now, if we restrict ourselves to circular orbits, which is not a bad restriction. You know, it would take a little bit of calculus to do elliptical orbits, or some, like an escape orbit, you know, to escape from Earth's gravitational pull and head over to the moon or head over to Mars or Venus or something like that. We could do that. But let's just say we're going to look at circular orbits, satellites, around our planet, and we're going to try to figure out what we need in terms of rocketry. And here's F equals ma, upper right. On the left side of this equation, the law of universal gravitation, G times m1 times m2 over r squared. And on the right is ma. Why do I say that? Well, the mass of the satellite, that's the m of ma. And then the acceleration is v squared over r. It's a circular orbit. We know what the speed is. We know what the distance of the moon's orbit is, or the satellite. Yeah, v squared over r, we got it. So that's it. Mass times acceleration, F equals ma. So here's the gravitational side, and over here is the centripetal force side. Right? Now, if you have something that's going straight down into the sun, and it's being attracted by the mass of the sun, and you have a satellite, and you just send it plunging straight down to the sun, you don't have a circular orbit. You just have an ma. And the a would be just the straight ahead acceleration. So you could use that as well. But for us, if it's a circular orbit, these are the equations to use. Now, let's get down to business on this. Do you see anything in here? Are you done with those?
Yeah, there was like half of them were right, and then the other half were like not supposed to.
Okay, did you write down the changes?
I left the scantrons were the ones that were wrong, and the ones that were right I just left the sheets.
Can you write it down on the summary page? The page that has all the students' grades on it. Okay. All right, now, do you notice anything in here that can get simplified? What do you think? MS, yeah. Let's blaze that out of there. All right, so go ahead and cancel MS. That's not too bad. That's good. So there's your leftovers. Anything else you can cancel? You can cancelize. Look at it carefully. Anything? Nope, you can't cancel the squares. What can blue shirt? You can get rid of an R. There's an R in the denominator on the right, and there's 2 on the left. So one of them's going to be left on the left, nothing on the right, and so you have G times capital M over R equals V squared. And hey, you guys, let me just move this up. That equation, if you think about it, is right-handy. Because the mass of the Earth is a constant, and Newton's constant, capital G, is a constant. We've got a good value for both of those. So it allows us to specify either the distance to the orbit R or the orbital speed. Question in the back. No, but it'll be on YouTube in a few hours. We're going to keep going. Question.
So is G the gravity at 9.8?
Capital G is it's not 9.8, but it's like that. It's a constant. It's like 6.67 times 10 to the minus 11 in the metric system. It's in the appendix of our book. It's a constant of nature, in fact. So think about this. If you know the radius, then you can figure out the required speed, v. And then you design your rockets appropriately to get to that speed. You know, you guys still got a lot of testing and stuff. You got to design everything, but if you know the radius that you want for your orbit, and you might say to yourself, Dr. B, they don't really care about the radius that much, do they? Oh, yes, they do, and here's an application. Suppose you want to have a satellite that orbits low enough that we can look into the back pocket of Putin and read his mail. Yeah, you want to have it good and low, nice and low. All right? And believe me, we can read their mail. And then, what was that? Was there a bunch of Russians over there? They can read our mail too. We both have pretty, like the Hubble Space Telescope. We can observe a basketball on the surface of the moon. So definitely they've got a bunch of Hubble. I guarantee it. A bunch of Hubble Space Telescopes turned the other way, looking down at the Earth, looking down the Russian's shirt pocket. Now, here's another example. Let's look at it the other direction. Let's say you want to have a certain orbital speed. All right? All right, you can figure out the required altitude. You know, how far to put that baby in orbit. You know, if you want it to orbit, you know, at 200,000 miles an hour, you got to put it at a certain. If you want it to orbit at 1,000 miles an hour, okay, you got to do a different size orbit. Because once you set up V, R is set. All right? Now, an example. All right? So now this is not a spy satellite. This is a satellite that many countries have, many companies have them. A satellite that orbits just once per day. So the Earth spins once and the satellite orbits once. Anybody know what kind of orbit or what kind of satellite that would be called? What is it used for? In the back. Oh, yeah? What, did you use X-ray vision or something like that? Yeah, that's right. Geosynchronous. He read the book. Gosh, darn it, students reading the book. Yeah, geosynchronous. And if you have DirecTV or any kind of a satellite TV system, yeah, it's you aim that antenna, and you get it aimed in just right, and you get a good strong signal, and then you just bolt it down in that direction, and you're good. Because the satellite is up, it's in motion around the Earth. It's just that the Earth is also spinning. So it's always up, and it always looks like it's the same point in the sky. You just got to get your satellite dish aimed in that direction, right? All kinds of telephone, television, radio signals go out by satellite up and down between geosynchronous satellites. You know what I think is kind of irritating on TV? You know, you're like watching the news, and the person in the newscaster asks a question, and then the reporters out there in Chicago or Los Angeles or wherever they are, somewhere else in Orlando even, and it takes them like a second or two to start talking and to give an answer. But that's because the signal goes out to the satellite and back down, and then the answer goes up to the satellite and back down. So it's a necessary delay. Geosynchronous communication satellites. And they're used for spy satellites as well. Now, another vocabulary term I want to make sure you're aware of is inverse R-squared force. The gravitational force in this theory of universal gravitation, we call it an inverse R-squared force because the distance dependence, R, is actually R squared, and it's in the denominator. Now, not all forces are like that. Spring forces, the distance that the spring moves is in the numerator, but for gravitation, it's in the denominator and it's squared. Now, one of the reasons that inverse R-squared forces are important is if it were any other power of R. So if it were R to the third in the denominator, or R to the 15th in the denominator, or R to the 37.073 in the denominator, it wouldn't have the significance. But a force that has R squared in the denominator, an inverse R squared force, is formally, mathematically speaking, infinite range. Let me repeat. The inverse R squared force is infinite range. We can prove it mathematically. And what that means is your left earlobe is interacting with everything else in the universe. You know, the Andromeda Galaxy, Pluto, the moon. It's interacting with your big toe. It's just that it's not a very strong interaction. The strongest interaction of your earlobe is with the Earth itself. And everything else is pretty weak. But yeah, when you go up to Ocala National Forest on a winter's night, you know, in November, on a camp out, and you're freezing your off, or you go, you know, I heard going down to the Everglades, out there where there's no city lights. If it's a clear night, you can look up and see the Milky Way just like in this picture. Raise your hand if you've ever seen the Milky Way. Oh my goodness. If you ever, you know what? If you ever go out west, if you ever go out to Colorado, up in the mountains, or Montana, or up into Canada, up in the mountains, or Alaska, if you go to Alaska, not only do you get to see the Milky Way, you get to see the Aurora Borealis on a good night. I mean, if the Aurora Borealis is running. But you always get to see the Milky Way on a clear night. So it's, thank you. So all those guys can pick up their printouts. Okay, all of you guys that brought your printouts down to be amended, and we got them squared away. So you can pick them up at the end of lecture. Let's keep going. I want to talk now about Edmund Halley and the famous comet that's named after him, Halleys Comet or Haley's Comet. I've heard it mentioned both ways. Now, he was a friend, a little bit older than Sir Isaac Newton, about 10 years older, but they were friends, good friends. And, so they talked together a lot. He was at Oxford and Sir Isaac was up at Cambridge, but they were friends. So that's like between us and USF down in Tampa. Oh, I don't even like thinking about that place. But anyways, so they were friends. And Edmund Halley had been having a discussion or conversation with other scientists about what force is it that keeps the planets on their orbits. And they couldn't come to a conclusion. Edmund Halley was thinking, we got to figure this out, because he was interested in astronomy, of course. He was an astronomer. And so he went to say, he said, I'm going to have to ask Sir Isaac. And so he went to Sir Isaac Newton and he said, Sir Isaac, what's the story with these planets? We just can't figure them out. And Sir Isaac said, oh yeah, I already figured that out 20 years ago. Universal gravitation. And universal gravitation, he proved mathematically that planets have to orbit the sun on, if they're in an orbit, it's either a circle or an ellipse. Okay, and a circle is a very symmetric version of an ellipse. He also said that the planets sweep out equal times or equal areas in equal times. Now on this diagram here, that means between 0 and 1 on the way around here counterclockwise, this little white kind of pie-shaped wedge here has the same number of square inches or square meters as this next one, between 1 and 2. This kind of bluish one here. And then the next one between 2 and 3, it's a little bit bigger, but it's narrower. And each of these alternating color, blue, white, Sir Isaac Newton said, yeah, if you organize the planet, so this is like month by month. Every month, the Earth sweeps out equal areas on its orbit. The same with Pluto, Jupiter, all the other planets. Then the third thing is, he proved mathematically that the average orbital distance and the orbital period, how long it takes to go around the Earth, or how long it takes to go around the Sun, the orbital period, they're proportional. If you square the period and take the third power of the average orbital distance. Now here's the fancy version of that third law. This is the third law of planetary motion. Capitals P stands for the orbital period. So P squared. And then little a, lowercase a over here, a to the third. That's the average orbital distance, also known as the semi-major axis for an astronomer. And then this stuff in the square brackets is a big constant of proportionality. And believe it or not, we still use this law here between the periods and the orbital sizes to figure out the mass of a black hole that we can't even see. But if we can see the things orbiting around the black hole, we can figure out its mass. Because the mass of the black hole would be one of these m's down here, two objects orbiting, M1 and M2. And then capital G, we got that. And good old pi up here, 3.1415, blah, blah, blah. Okay, we got all those numbers. So if you can figure out those measurements, you can really use that law. Now, Sir Isaac Newton said, yeah, I got the three laws. I got all these three laws of motion. It's a lock. That's what the planets are doing. What are you talking about, Edmund? So Edmund said, yeah, okay, thanks, Sir Isaac and Mr. Smarty Pants, but how about comets? And so that's what Sir Edmund Halley surmised. He said, I think that comets also follow elliptical orbits just like a planet. They're not planets, but they behave on the same dynamical basis. They should return periodically. You know, the planets go around the sun. You know, they have an orbital period, so why not comets? So what he did was he went back and cataloged as many, so he went to the library. You know, he looked through all the historical archives of ancient astronomy, you know, and he tried to get as many comet dates, you know, how long they were visible and everything, for as far back as he could go. And he went back a ways because even 500 years, 600 years, he was able to get some dates. And here's three comets that he predicted are actually the same. I inadvertently stopped the recording. Okay. It returned on Christmas Day. Amazing. 1758. Now, those two guys were long gone. But it was a huge verification. So make a note of that. Halleys Comet. Big, big verification. That's what science does. It tries to predict the behavior in the future of some kind of a physical system, in this case, a comet. And by God, it came right on time, right on the money. Halley was right on the money. 1758. So put a big check mark in the win column for those two guys. And we're going to be talking about Sir Isaac Newton and the law of universal gravitation for quite a while. We could spend an entire year talking about it if we wanted to. But now I want to spend a few more minutes with you talking about the skateboard interaction. And this is in chapter 4, the very beginning. And I'm going to bring in some concepts that'll bring it all together. And, you know, sometimes you're trying to get through, you're trying to, you know, make a good go of things, and you just need one thing to bring it all together. And so let's look at this example of the two skateboarders from page 46. By the way, some of those comments about gravitation, they are not in the book, so make sure you have them in your lecture notes, either now or after you go back and study the YouTube. Okay, Carl and Bob. Carl was 40 kilograms and he started from rest. Bob was twice that mass, two imaginary guys, one twice the mass of the other. And they push off, just like the two, Isabel. Was it you? Are you here? You're Isabel? Where's Isabel? Where's the skateboarders that were skating the other day? I don't. They're cutting class. Anyway, when those skateboarders were up here in the front and they did patty cakes and pushed off from each other, I went 1, 2, 3, go, and they pushed off. That's basically what we're looking at here. So we have a force, magnitude 500 newtons. So Bob pushing on Carl is going to be 500 newtons to the right. Carl pushing on Bob is going to be 500 newtons to the left. And let's signify those newtons with a minus sign. Leftward newtons with a minus sign. And they stay in contact for a certain amount of time. So I just dreamed up these nice round numbers for the textbook. This is from page 46, right in there. So I said, all right, let's try 0.48, fraction of a second, nice round number. But everything, you know, no matter what the interaction time is, you can do the same calculations that we're about to do. Okay, accelerations. Acceleration is the force divided by the mass. Force is 500 divided by 40 kilograms. That's the acceleration that Carl feels. Okay, so the force of Bob on Carl is 500 newtons divided by 40 kilograms. That's 12.5 meters per second squared. That's a little bit more than a g of acceleration. Okay, g is 9.8. It's a little bit more than that. By the same token, Bob is getting 500 newtons to the left with a minus sign, but his mass is 80 kilograms, and so, excuse me. So his acceleration is negative 6.25 meters per second. Next thing we're going to do is figure out, all right, what's their delta V? They start at rest, so they don't have any velocity to start, just like our two skateboarders up here in front of the classroom. But how much velocity do they acquire? Well, for Carl, it's 12.5 meters per second squared of acceleration times the interaction time, 0.48 seconds. Right now, for Carl, that works out to 6.00 meters per second, and it's to the right. Bob, on the other hand, has a smaller acceleration. It's to the left, so it's negative. But the interaction time is the same, 0.48. This is kind of interesting. You might want to make a note of it. The interaction force and the interaction time are the same. But the velocity states are not. Let's look at the final velocity state. He started at rest, so Carl's final velocity state is 6.00 meters per second to the right. And Bob's is going to be a little bit less. It's slower, 3.00 meters per second negative, i.e. to the left. And so the question you may ask yourself, Dr. B, what is all this business about equal but opposite reaction? I don't see equal but opposite velocities. Yeah, the forces, the interaction time are equal, but the velocities aren't. Doesn't that disprove Sir Isaac Newton? Well, let's take a look. Let's build up some let's build up some support for Sir Isaac Newton. I mentioned that the force and the elapsed time are equal. Go ahead and take your calculator. Oh gosh, we forgot to turn on the... Hold on a second, you guys. Here's your question. What's the product of an interaction force, 500 newtons? They both get an interaction of 500 newtons, just one of them is leftward. Product of interaction force and elapsed time, 0.48 seconds. Multiple choice. Force times a time. 20 seconds. 15 seconds. 10 seconds. 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. All right, let's see what you guys voted for. Wow, look at this. We got a little bit of explaining to do because there's a spread in the answers. Let's take a look at what we got here. Okay, there's the answer, 2.40. Go ahead and write that down, a Newton second. And just jot down this for your notes. 1.0 Newton seconds is the same as a kilogram meter per second squared times a second. So 1 unit of seconds gets canceled, and you're left with kilogram meter per second down here. And hey, you guys, that's a mass times a speed. mass times the velocity. Go ahead and make a note of that. It is not a coincidence. A force times the time is a kilogram meter per second. Yeah, we want to know all about that bad boy. Question number 2. You ready? Question 2. Now, m delta v over delta t. We talked about that last Tuesday as well. One of the forms of Newton's second law. All right, if that's true, then what is F times delta T? I mean, F times delta T is equal, but opposite for Bob and Carl. But what is it equal to? What would it be left? What would the leftovers be? "20 seconds. "10 seconds. 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. All right, see what you guys. Good. That's the correct answer. And what I want you guys to do is write down this equation. F delta T equals m delta V. That's also known as the impulse equation. And it's pretty important for us. F delta T, those are the things that are equal for the interaction. Interaction forces are equal. Contact time delta T is equal, of course. And what we're going to do now is keep branching out from Newton's 3 laws of motion from one. This starts at letter B. It should be 1A and 1B. Anyways, skateboarders are in contact for a set amount of time, delta T. Interaction forces are the same. So F delta T must be equal for each of them. So the force of Carl on Bob times delta T is equal to the opposite of the force of Bob on Carl times delta T. And that is actually the basis for expressing exactly equal but opposite reaction. Question?
The previous formula that you showed, what is that for again?
This is impulse formula. We'll get to we got some more slides here. Don't worry. Now, m delta v. M delta v. What does that correspond to? It corresponds to something that we now call the change of momentum. If momentum is defined as mv or vectorized, here's the vectorized version. Here's delta p. M times the change of delta v. The mass is a scalar and it's a constant for us. Now, the guys down at Mission Control, those rocket scientists in Houston, a rocket doesn't have a constant mass. As long as that rocket motor's burning, it's losing mass out the tailpipe, a lot of it. And so as these rockets launch from Kennedy, they're losing, the mass is changing every inch of the way that they go up. It's very difficult to calculate. But for us, we're going to be working with stuff that has a constant mass. Okay, so you could say that the momentum exchange, delta P, is the same for each guy, equal but opposite. Or you could say that Newton's third law holds. So here's another way of writing Newton's third law. Delta P for Bob is equal to minus delta P for Carl. And that is because F delta T is equal to delta P. And yes, that equation, F delta T is known as the impulse. And delta P is known as the change in the momentum. So let's talk about this concept, the impulse. F delta t. Okay. Sometimes you see it written as F times t. I usually write it as F delta t. Okay. That equals F, and that equals delta p. Right? The change. So in other words, the change of momentum is equal to the impulse. Change of momentum is equal to F delta t. And hey, you guys, this is another This is another version of Sir Isaac Newton's second law. F equals ma. In fact, this is the way that he wrote it. And you can read more about that in the textbook. Now, the last few minutes of class, I want to spend calculating a problem with you. I want you to take careful notes. We're going to calculate a stopping time. On homework 5, I believe it was, we had a problem where you were to calculate the stopping time of an object under a force. And that's what we're going to do now. And you're going to need this for your homework. So let's take a look at it. Here it is. Given a coin of mass 0.05 kilograms, sliding across the tabletop from left to right. At initial point x1, its speed is 1.7 meters per second. Rightward. And then it experiences a frictional force 0.02 newtons leftward. It slows down to a stop at position x2, which is now out of the picture. What's the stopping time for this coin? We had that problem. We're going to do another version of it tonight in your homework 6, which will be running right after class. And so here's how we're going to attack it. We're going to use momentum, and we're going to use the impulse equation. The impulse equation is the best way to tackle, usually, a stopping time problem. So we'll figure out P1 and P2, get delta P. And then for the impulse part, F delta T, we're going to use the friction. And we're going to use a minus sign for the frictional force. So here we go. Let's get P1 and P2. All right? P1, the mass times the velocity, 0.05 kilograms times 17 meters per second, rightward. And then that multiplies out to 0.085 kilogram meters per second. P2 is easy, 0. Because it starts at, or not, it starts at rest. It stops. It comes to a rest. So P2 is 0. All right. Those two values allow us to figure out delta P. Here we go. Delta P is P2 minus P1, so it's 0 minus 0.085 kilogram meters per second. So delta P is negative. You've lost momentum, all right, from the friction force. So now we're going to hook that up to the friction force part of the equation. So here's the impulse equation, F delta T. And that's going to be equal to the change in momentum. And so here's my change in momentum in the lower right, negative 0.085 kilogram meters per second. And over here, I don't know what delta T is. That's my stopping time. But I do know what the friction force is, negative 0.020 newtons. And you can cancel the negative signs if you want, right down there. But we're going to just go to the next page and finish this up. So here we go. The last two equations here, I'm going to park them up here at the top. All right. There's the impulse equation. And we've plugged in our known values. Gotten a delta P. Now to clear this, we divide both sides by negative 0.020 newtons. Both sides. And here's the division problem. So delta T, now you just compute. And your answer is 4.25 seconds. And if you were doing the homework, you type it in as a 4.3. Now, we're going to dismiss, it's 1:18. you have homework 6, and I'll leave this up on the screen for you. You have homework 6 to work on tonight. It's fairly short, but it does involve some stopping time and some other stuff. All right, I'll see you on Thursday. You're dismissed.